This is a quick video on section 12.7 where we are doing the quadratic approximation. Okay. The formula for this we've written down a couple times in class, but it's q of xy for quadratic approximation. It will be the function evaluated at x naught, y naught, plus the gradient of the function evaluated at x naught, y naught, dot product with x minus x naught, y minus y naught. And that piece right there makes the linear approximation. And then we have to add on to that linear approximation a term that has squared terms to get the quadratic piece. So that will be 1/2 the Hessian of the function evaluated at x naught, y naught. And then you need to multiply by x minus x naught, y minus y naught. And then you need to take that result and multiply it again by x minus x naught, comma, y minus y naught. Okay. So I will, the new thing for this section is, new to this section is doing matrix, because the Hessian is a matrix vector multiplication. This piece right here is a vector. This x minus x naught, y minus y naught is a vector. You could think of this as a difference vector, and you need to multiply this by the Hessian matrix. So just a quick example on matrix vector multiplication. Okay, and then I'll show an example of what this quadratic approximation is doing. Okay, so just a quick example. Let's say that you have some matrix A, I'll call it A, and it's the vector 1, 2, 3, 4, the matrix 1, 2, 3, 4. So you can view this as two vectors stacked on top of each other, where the vector V is the vector 1, 2, and the vector W is 3, 4. So you can kind of view this matrix as two vectors stacked on top of each other. Now let's say that you pick a vector like u. Let's let u be another vector. And let's say that it's the vector 5, 6. Okay, so if you're going to do A times u, the result of that is going to be another vector. It's going to be another vector, blank, comma, blank, where you need to fill in the blanks. Okay, and what goes in this first blank is the vector v dotted with u. That will be a number. Right? And then what goes in this second entry is the vector w dotted with u. Notice I'm just taking the vectors that make up the matrix A, and I am multiplying them with each other. That is one way to think of the result. If you've had linear algebra before, you may prefer to think of multiplying this matrix and this vector by doing this vector, this row times this column, and you would get 1 times 5 plus 2 times 6. You would get 1 times 5 plus 2 times 6. And then you would do 3, 4 times 5, 6, which would be 3 times 5 plus 4 times 6. But that's just a fancy way of saying v dotted with u, and then w dotted with u. Okay, so then the answer to a dot u would be 5 plus 12, is that 17, 15 plus 24, 15 plus 24, whatever that works out to be, 39, right? You could then go through and then multiply that matrix again, a dotted with u times u, and then you would get 17, 39, and then you'd have to dot that again with 5, 6, which would give the number 17 times 5 plus 39 times 6, and whatever that number comes out to be. So there's a quick example on doing matrix times a vector, and then doing a matrix times a vector, and then multiplying by a vector again. Hope you can see why we're going to need to do that here, because we're going to have the Hessian matrix multiplied by a vector, and then we're going to have to multiply that by that same vector again. Okay, so here's a quick example on the next page. Let's say that I'm going to look at the function f of xy is equal to e to the negative xy. Okay, now you know that what you need to do the quadratic approximation, to find the quadratic approximation, you need the first derivatives. You need the first derivatives, and then you need the second derivatives. Okay, the first derivatives are given by the gradient, and the second derivatives are given by the Hessian. And all those just mean that you need to compute partial derivatives. So I will leave that to you. Okay, let's say that we are going to look at the point x naught, y naught. What point x naught, y naught did I pick? I picked 0, 0. So let's pick the point x naught, y naught to be 0, 0. Okay, so that is your point. So essentially what we're doing here, and I'll show a more reasonable, less sketched picture in a second, but we are computing the function, looking at the function f of xy, given by this specific example. We have a point x naught, y naught that we have been given, and we are trying to find at this point some sort of quadratic that approximates this function at that point. We know what the tangent plane looks like. We know the tangent plane can approximate this, and that would use only the first derivatives. In the linear approximation, that would only use the first derivative terms. But to compute the quadratic terms, you need to bring in the second derivative. So compute the gradient, compute the Hessian, then second step, evaluate the gradient at the point x naught, y naught, evaluate your Hessian of f at x naught, y naught, and then 3, use formula and matrix vector multiplication from above. Okay, what I mean by above is this formula that we just wrote down. Okay, and this matrix vector multiplication. So let me scroll over here to an example real quick, and you can see what is going on here. So here's our function, e to the negative xy. I picked a point x naught, y naught to be 0, 0. I will leave you to check these computations, but here is the gradient vector, negative y e to the xy. This is my, this term right here is the partial derivative of f with respect to x. This entry is the partial f with respect to y. This entry of the Hessian right here is f sub xx. This entry of the Hessian is f sub xy, the partial derivative of f with respect to x, and then multiply, and then do a partial derivative with respect to y. Here's f sub y. And then when you take this Hessian and evaluate it at 0, 0, you get 0, negative 1, negative 1, 0. Okay? So you can do these computations to compute the derivatives, and you can evaluate the gradient and the Hessian at those points, at the x naught, y naught values. What I want to show you the computation for is how to get the linear approximation. Here's the answer, it's 1, and here's the quadratic approximation, it's 1 minus x times y. What makes this a quadratic approximation is that we have x multiplied by y terms. That's x to the first multiplied by y to first. That is a total power of 2, which makes this a quadratic approximation. So over here you can see a plot just so you can see what you're going to be computing. In gray, that is your function. Notice how it curls up on the sides. Here's your linear approximation at 0, 0. And if you were to zoom in on this point, you would see that that plane is a good approximation of the function at that point. But if you go to the quadratic terms, you can see how the quadratic term actually has some bend to it. So that function that we're seeing in blue is actually trying to bend to match the function. Okay, it's not exactly equal to each other. The blue function is not exactly the gray function because we're only doing a second Taylor approximation. So what I want to show now is how are we getting these formulas right here. Okay, so let me move this over to the previous page. Okay, and let's bring in a blank piece of paper here. Let's see what we're looking at. Okay, so it looks like we have our gradient of our function at x naught, y naught. That is 0, 0. Okay, we have our Hessian of our function evaluated at x naught, y naught. Okay, and that gives us 0, -1, -1, 0. Okay, I'm just reading this off. Our function value, our function is e to the negative xy, so that our function evaluated at x naught, y naught, that will be e to the 0, which is 1. Okay, so that's all we need from this table, and we need to compute our formula that was above. Okay. So I will go through that step now. We need to, the linear approximation is just the function evaluated at x naught, y naught, plus the gradient evaluated at x naught, y naught, dot product with x minus 0, y minus 0, because this is our x naught, 0 is y naught. So we have 1 plus our gradient was 0, 0, dotted with x, dotted with y, and you will get 1 plus 0 times x plus 0 times y, which is just 1. And that's what we were seeing in our previous picture. We just had a flat plane. Right? We had just a flat plane, right? Always at the z value of 1 here. You can see that. Okay, so let's move on to the quadratic piece. Okay, so our quadratic approximation, q of xy, is going to be our linear approximation piece plus 1/2. Our Hessian was 0, -1, -1, 0, multiplied by x, multiplied by y, and then I had to multiply that thing by xy again. Okay, so you will get 1 plus 1/2. And now we need to compute this thing real quick, okay? So if you take this vector dotted with xy, okay, our result, okay, this xy is this xy. I'm just bringing it down. I'm not using it yet. I'm multiplying this matrix times this vector, and that will give negative y. -1, 0 dotted with xy is negative x. Okay, so now you continue on. You will get 1 plus 1/2. Now dot these two as vectors, and you will get minus xy, which is otherwise known as minus 2xy. And then the 1/2 and the 2 cancel, and you'll get 1 minus x times y. That's x to the first, y to the first. They have a combined total power of 2, which makes this a quadratic function in 2 variables. Okay, and that is what we were seeing in. That's what we were seeing in this plot over here. That blue, if you plot 1 minus x times y and plot the function e to the negative xy on the same set of axes, you will see that plot right there. And so ends our example with doing the quadratic approximation of the function f of x, y is equal e to the negative xy at the point x naught, y naught is equal to 0, 0. Change the point, the function, the quadratic approximation will change. Change the function, the quadratic approximation will change. And I will leave you to do more homework problems to try other problems.